These are the answers to the practice quiz on kinetic molecular theory and gas laws. For these first 10 questions, you have to decide if the statement is true, and if so, you just write true. But if the statement is false, then you have to decide what the underlined words should be changed to make the statement true. So in this first question, examples of elements that exist as diatomic gases. Well, neon is not a diatomic gas. It is a monoatomic gas because it doesn't form any bonds with itself. The diatomic elements include hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. But we're looking for gases at room temperature. And since bromine is a liquid and iodine is a solid at room temperature, that leaves hydrogen, nitrogen, or chlorine. All of these would have been acceptable choices to change the underlined portion to make it true. In our next statement, the word homogeneous is underlined. A homogeneous mixture has only one phase of matter and appears to be uniform throughout. Air is a homogeneous mixture, so that statement is true. The next one talks about oxygen, 1 mole of oxygen at STP, standard temperature and pressure. It says it has a volume that's twice as much as 1 mole of methane, CH4, which is also at STP. Well, 1 mole of oxygen at STP should have the same volume as 1 mole of methane, and that's because if you have the same moles, the same temperature, and the same pressure, then the volume should be the same as well. So what exactly is twice as much for oxygen compared to methane? If you look on the periodic table, 1 mole of oxygen weighs 32 grams, but 1 mole of methane weighs only 16 grams. So I was going for either mass, or you could have said molar mass, or density to change that statement to make it true. In number 4, it says that the average kinetic energy of the gas particles depends only on the absolute temperature of the gas. Let's take a look at the various postulates or statements of the kinetic molecular theory, or the KMT for short. One of the statements is that the average kinetic energy of the gas particles is proportional to the absolute temperature. So therefore, statement number 4 is true. Number 5, airbags are used as safety devices because air cannot be compressed easily. Well, gases, in general, are very compressible because there is a lot of empty space between the gas particles. So let's change the underlined word to can. All right, number 6. If the volume of a fixed sample of gas is reduced by half at constant temperature, the pressure exerted by the gas will be doubled. This statement is consistent with Boyle's law, which shows the inverse relationship between pressure and volume. So statement 6 is true. Number 7, we're changing the temperature of a gas from 10 degrees Celsius to 500 degrees Celsius. The volume will increase. So the question is it going to increase by a factor of 50? And the answer is no, because when we do mathematical relationships and calculations involving gas temperature, we should always change our units into Kelvin, not Celsius. So the relationship is that it goes from 283 Kelvin to 773 Kelvin. The volume of the gas sample will increase, but we're looking for a ratio between 773 and 283. So that ratio is not a factor of 50. The volume will increase by a factor of 2.73. Number 8, let's take a look at the statements of the KMT one more time and talk about attractive forces between gas particles. So again, these are the statements of the KMT, and the attractive and repulsive forces between gas particles are assumed to be not important or negligible. So statement number 8 is true. Number 9, the distances between the gas particles, are they much larger than the sizes of the gas particles themselves? Again, back to the KMT, the volume of the gas particles themselves is much smaller than the volume occupied by the gas. So the gas particles are much farther apart. We can assume that the volume of the individual particles is very small. Statement 9 is true. And then finally, statement number 10. Did Torricelli invent a device known as a manometer, which has to do with a tube filled with mercury and placed upside down? Well, in the 17th century, Torricelli invented the barometer, and we're describing its properties here. So we're going to change the underlined word from manometer to barometer. Now, what is a manometer? You're going to see an example of one coming up later on the practice quiz, so we'll take a look at that. All right, number 11. For a fixed sample of gas, the pressure on the gas is increased. What happens to the volume? Again, this is Boyle's law, the inverse relationship between pressure and volume. Pressure goes up, volume goes down, so the volume will decrease. Number 12, if we add more gas, so we're increasing the number of moles, the container has a constant volume, and the pressure, is it going to go up or down or stay the same? Well, if we add more gas to a rigid container, we'll increase the frequency of collisions between the gas particles and the container walls. Number of moles and pressure are directly proportional. So if moles go up, the pressure goes up as well. Number 13, the temperature is increased. Now, will density decrease, increase, or stay the same? So what's not changing here is the mass. We're not adding any more gas to the container, and it says that volume is constant. Since density is mass over volume, the density should stay the same because neither of those quantities, mass or volume, is changing. Number 14, temperature goes up. Well, pressure would go up as well in this case because we're increasing the temperature of the gas. That causes the molecules to move faster, increasing the frequency and the force of the collisions between gas particles and the container walls. So temperature goes up, pressure goes up. Number 15. Temperature goes up. What happens to the volume? So Charles' law says that temperature and volume are directly related. So when temperature increases, the volume increases as well. So we're talking about changing two variables and holding the other two constant. So what's not changing is pressure and number of moles. But when temperature goes up, volume goes up. Number 16. Do all gases have similar chemical behavior? Well, some gases are going to catch on fire. Others can actually put out a fire. So statement A is not true. Are composed of molecules. Well, noble gases, as we saw earlier with neon, noble gases, helium, argon, they're monoatomic, so they're not composed of molecules. And not all gases are less dense than air. Some are going to be heavier and sink, like carbon dioxide or sulfur hexafluoride. Other gases might be less dense, like helium or hydrogen. But since the particles are far apart, all gases can be easily compressed. Number 17. Gas particles are separated by relatively large distances, so that means that they should be relatively easy to compress, so the correct answer is not C. Gas particles do not experience strong intermolecular forces, so the correct answer is not D. Now, although gases do exert more pressure when they're heated, it's not because they're far apart, it's because they move faster. A given mass of gas particles occupies a relatively large volume, so since density is mass divided by volume, gases have relatively low densities. Number 18, we're going to take a rigid container and add more gas to that container. So because we're going to increase the number of moles, the pressure increases. So we doubled the moles and we doubled the pressure. Which of these statements explains why the pressure increases? Well, notice that we're not changing the temperature. And so if we're not changing the temperature, that means we're not changing the kinetic energy or the speed. But we are increasing the number of collisions because we have more moles of gas. So correct answer is B. Number 19. We are compressing a gas at constant temperature. So therefore, what's not changing would be the amount of gas because we're merely compressing it. We're not causing the gas to leak out of the container. And since the amount of gas, either mass or moles, is not changing, we can eliminate choices A and C. Are the particles traveling faster? Well, we're still at constant temperature, so they're not traveling faster, but the density, mass divided by volume, would increase. We have the same mass in a smaller volume. So density increases. The correct answer is D. Number 20 requires us to do some unit conversions. So we know that 1 atmosphere is equal to 14.7 pounds per square inch, or psi. It's also equal to 101.3 kilopascals. It's equal to 760 millimeters of mercury, or 760 torr. Let's go ahead and decide to convert everything into one unit. I chose atmospheres. So for letter A, we have 1.52 atmospheres. For letter B, if we convert 25 psi into atmospheres, we have 1.7. Since we're looking for the value that has the largest pressure, the correct answer could not be A. Let's see if anything is larger than 1.7 atmospheres. For letter C, 165 kilopascals is equal to 1.63 atmospheres, so C is not correct. And then letter D, 1250 torr is equal to 1.64 atmospheres. So the correct answer is B. Number 21. Now we're trying to increase the speed of the gas particles, and the only way we can do that is to raise the temperature of the gas, which will increase the average kinetic energy of the gas particles. So correct answer is D, because temperature is increasing. Number 22, this represents pressure and volume. This is a Boyle's law problem, so P times V equals P times V. The initial pressure is 4 atmospheres. The initial volume is 10 liters. The new pressure is, we don't know, at least not yet, and the new volume is 8 liters. So when we do the math, we're doing pressure equals 40 divided by 8, so the answer is 5 atmospheres. Number 23. This involves temperature and volume. This is a Charles law problem, so V over T equals V over T. But be careful to convert your temperature into Kelvin. So 30 degrees Celsius is 303 Kelvin. 120 degrees Celsius is 393 Kelvin. Let's plug in the numbers. So 5 liters is the initial volume, and the initial temperature is 303 kelvins. The new volume is we don't know yet, and the new temperature is 393 kelvins. So the new volume is going to be 5 times 393 divided by 303, and that gives us an answer of 6.5 liters. Number 24. This involves pressure of a gas mixture. This is Dalton's law of partial pressures, which says that the total pressure of the gas mixture is equal to the sum of the individual partial pressure of each gas. In this mixture, the two gases are oxygen and nitrogen. Now we have different units of pressure. We have millimeters of mercury and we have kPa. So we have to convert everything into one unit. I chose millimeters of mercury because the answers are listed with that unit. So 101.3 kilopascals is the pressure of the oxygen. That is also equal to 760 millimeters of mercury. And since 800 millimeters of mercury is the total pressure, and 760 is coming from just oxygen alone, that means that the pressure of the nitrogen must be 800 minus 760, or 40 millimeters of mercury. Number 25. Now we have a picture of what a manometer looks like. It measures the pressure in a sealed flask by comparing it to the pressure of the atmosphere. So currently in the open tube, the pressure of the atmosphere is 760. So we have to consider the diagram and the different levels of mercury. Is the pressure in the flask greater than 760? Well, the answer is no. The pressure in the flask would be less than the atmosphere. The atmosphere is pushing the mercury down lower on the left side. That means that the atmospheric pressure is greater than the pressure in the flask. So the correct answer is either A or B, because it says the pressure of the gas in the flask is less than the atmospheric pressure. Well, what's less than 760 would be 760 minus 150, and the answer is 610 millimeters of mercury for the pressure inside the flask. Number 26 is a very easy conversion from Celsius to Kelvin. All you have to do is add 273 to the Celsius temperature. And so we get an answer of 223 kelvins. Question 27 is giving us a data table with pressure and volume. This involves Boyle's law. We're given 2 data points, and we have to fill in the missing information. So this data point has a pressure of 2 atmospheres and a volume of 50 milliliters. This data point has a pressure of 4 atmospheres and a volume of 25 milliliters. If we use Boyle's law, 2 times 50 equals 4 times 25. So far so good. Now we have to calculate the pressure in that next row of the data table, since 4 times 25 is 100, and that equals the new pressure times 12.5 milliliters. The new pressure is 100 divided by 12.5. That gives us a pressure of 8 atmospheres, and we could plot that on the data table, on the graph. We could plot that at a pressure of 8 and a volume of 12.5. So we're starting to see that curve showing the inverse relationship between pressure and volume. Now, of course, since 10 times 10 is 100, then we can fill in that last bit of information and we can plot that last data point, and you can definitely see the curve and the inverse relationship between pressure and volume. So P times V equals P times V. That's how we solved the data to get the missing information. Okay, now on to number 28. This is about Charles' law. So that's volume over temperature equals volume over temperature. Remember that temperature should be in kelvins. So 20 degrees Celsius becomes 293 Kelvin. 40 degrees Celsius becomes 313 Kelvin. And negative 20 degrees Celsius becomes 253 kelvins. All right, so if we're doing V over T equals V over T, 100 milliliters divided by 293 kelvins is equal to the new volume divided by 313 kelvins. And when we solve, we do V2 equals 100 times 313 divided by 293, and we get 107 milliliters. In the next example, 100 over 293 equals V2 over 253. So that means we do the math, 100 times 253 divided by 293, and we get 86 milliliters. All right, number 29. This happens to be a Boyle's law problem because it involves pressure and volume. But the initial pressure is in units of kPa, and the final pressure is in units of atmospheres. So we have to decide which units to use. I'm going to choose atmospheres. So I'll take 75.0 kPa, and I'll convert that into atmospheres. I get 0.740. If we're doing P times V equals P times V, the initial pressure is 0.740 atmospheres. Initial volume is 2.50 liters. The new pressure is 2.60 atmospheres. And the new volume works out to be 0.712 liters. Now, if you're concerned that you did it differently because you chose kilopascals it would look something like this. Let's convert 2.60 atmospheres into kilopascals. So now we have 263. We're still going to do P times V equals P times V. The new volume would be 75 times 2.5 divided by 263. And we get an answer that's pretty close to what we had earlier, just based on rounding. So 0.712 or 0.713 would both be correct. Okay, let's take a look at number 30. This sounds like a Charles law problem because we see temperature and volume. Again, watch out for Celsius and Kelvin. So we have 10 degrees Celsius, but that really is 283 Kelvin. And also watch out for volume. We have 925 milliliters and 1.25 liters. So it's your choice. Either you can say what I did, which is I used 925 and 1250 for my volumes, but you could have done 0.925 and then 1.25 for liters. If I do the math to solve for the new temperature, I get 283 times 1250 divided by 925. That's a new temperature of 382 Kelvin. And when I subtract 273 to go back to Celsius, I get my answer of 109 degrees Celsius. But had you done this problem by leaving the temperature in Celsius, you definitely would have gotten the wrong answer. All right, moving on to number 31. This involves Dalton's law of partial pressures. We have the total pressure, which is 1.01 atmospheres, and that is a mixture of nitrogen and a little bit of water vapor. So the water vapor has a variety of values in the table. We can look up the pressure of water for the specific temperature that the experiment is using. So in this case, 20 degrees Celsius. Our total pressure is in atmospheres. Let's convert that to torr. So we get 767.6 torr, and that is equal to the total pressure of the mixture of nitrogen and water. Now we're at 20 degrees Celsius, so the pressure of the water is 17.5. To figure out the pressure of the nitrogen, all we have to do is subtract 767.6 minus 17.5. That gives us a pressure of the nitrogen, 750.1 torr. Okay, on to number 32. We have a mixture of gases, helium and neon, but they're in grams. Let's convert from grams to moles. Looking at the periodic table, 1 mole of helium weighs 4.00 grams. 10 divided by 4 is 2.500 moles of helium. In a similar way, 1 mole of neon weighs 20.18 grams on the periodic table. So do the math, and we get 1.500 moles of neon. Well, now that we know the moles of each gas, how does this help us figure out the pressure of each gas? 640 kilopascals is the total pressure of the gas mixture. We should know that the more moles you have, the greater the pressure is going to be. And that doesn't matter whether it's helium or neon. So because the pressure of each gas is proportional to the moles, then we can definitely compare the mole ratio and have that be the same as the pressure ratio. So the mole ratio is 2.5 to 1.5 or 5 to 3. If the ratio of moles is 5 to 3, so helium to neon, then the ratio of the pressure of helium to neon should also be in a 5 to 3 ratio. That means that if 5x is the pressure of the helium, then 3x is the pressure of the neon. And if we add 5x plus 3x, we get 8x equals 640 kilopascals. 640 divided by 8 is 80. So if 5x is the pressure of the helium, then 5 times 80 is 400 kilopascals. And if 3x is the pressure of the neon, 3 times 80 is 240 kilopascals. Now you might have set up your proportion or your ratio a little bit differently than I did, but hopefully you got the correct answer. And hopefully this method makes sense, that the pressure ratio had to be the same as the mole ratio in this gas mixture. All right, moving on to number 33. A gas sample has a volume of 456 milliliters and a pressure of 1.25 atmospheres and a temperature of 25 degrees Celsius. Now we're changing the pressure and the temperature, so we can't just use Boyle's law, which is pressure and volume, and we can't just use Charles' law, which is volume and temperature. So we have to write an equation that combines these two laws together and contains 6 variables. We call this the combined gas law equation. It involves P, V, and T, and it's pressure times volume divided by temperature. So now we have these 6 variables. We can go ahead and plug in everything we know in part B. So the initial pressure is 1.25 atmospheres. The initial volume is 456 milliliters. The initial temperature is 25 degrees Celsius, but we have to convert that to Kelvin. So 25 plus 273 is 298 kelvins. The new pressure is 1.35 atmospheres. The new volume is, we don't know yet, and the temperature has gone up by 10 degrees Celsius, or in this case 10 Kelvin. We go from 298 to 308 Kelvin. When we solve for the new volume, we're going to multiply both sides of the equation by 308, and we're going to divide both sides of the equation by 1.35. So the setup looks like this. And when we plug all this into our calculator, we get a new volume of 436 milliliters. Now, in part C, we've got to decide which of the following changes had a more significant impact on the volume of the gas. The new volume is 436 milliliters. Let's consider each change separately. So if we had just increased the pressure, we would have predicted that the volume should decrease based on Boyle's law. On the other hand, if we had just increased the temperature, the volume should have increased based on Charles' law. And since those changes are going to affect the volume in different ways, the correct answer has to do with what really happened to this gas. So because the new volume had decreased, that means that the pressure change had a more significant impact on the volume of the gas. So the volume of the gas actually decreased as a result of these changes. So therefore, the increase in pressure had a more significant impact on the gas than the increase in temperature. All right, well, that wraps up the practice quiz on the KMT and gas laws. I hope that those explanations were helpful. Thanks for watching, and good luck studying for your quiz.